Good morning, everyone. I'm Feng Wang from the Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. First, I would like to extend my sincere thanks to the Professor Kihoff and Professor Li for their kind invitation and organization. And today, I will sharing AI-driven behavioral analysis system developed by our lab in the course of studying the sex differences in the neuroethology. Yeah, as we know, the natural intelligence comprises a set of adaptive solutions that enable animals for their survival and reproduce within the specific environment. By exploring a data-driven research method to analyze its neural mechanisms and digitally represents its fundamental principles, we can not only deepen our understanding of the digital coding characteristics of life, but also lay the groundwork of the next resolution of the artificial intelligence. Our team investigate natural intelligence through the neuroethology. What is the neuroethology? Which emphasizes the study of the natural behavior, those shaped by the natural selection, rather than the behaviors specific to the brain states or the laboratory experiments. Study how the neural systems process the biological stimuli to generate the natural behavior, enhance our comprehension of natural intelligence. As we know, there are well-spread sex differences in natural behaviors, such as the individual survival, but also the species reproduction. Beyond that, humans also exhibit the specific sex difference in the emotions, behaviors, and susceptible to the certain disorders. These differences are further amplified in some of the mental disorders. There are incidents where the incidence rate in females is 2 to 4 times higher than males. However, in the basic research, there are lack of the data from female subjects. Nearly 80% of studies use only males. Drugs or therapeutic interventions developed under such biased strategy may be ineffective or even cause side effect in females. So, since 2014, multiple institutes have emphasized that the preclinical studies must include the data from both male and female animals and cells. So the key question our team explores are: what exactly are the behavior differences in neuroethology, and what the underlying mechanisms underlies these differences? Today's my presentation will focus on the first part. When we study the laboratory animals instead of human patients, although similar experiments we can perform, but the absence of the inquiry and the chief complaints, it means that we must design appropriate behavioral paradigms and conduct carefully interpretation. In the traditional behavior analysis method, research include a directly observation in the wild, or a single camera fixed in somewhere, or use of various sensors. When we go to the movies, the video data can be then analyzed by manually or use some computer softwares such as animes. However, these kind of the traditional behavioral analysis have their limitations. The animals often amplified as a single point, which leads a loss of post informations. And the single camera sets point to occlusions. Moreover, the analysis often rely on the unprovocable set threshold. For example, when we test the freezing behavior, when the freezing duration defined as 3 seconds. How about 2 or less? Yeah. In the recent years, there has been a growth call for the AI assistant analysis in neuroethology to uncover the hidden information behind animal behaviors. In the recent years, the AI assistant behavior analysis has advanced significance in the past few years, lead to the tools such as the Deep Lab Card, Mosaic, Dance, and Behavior Atlas. But how we can do when we get the vast behavioral data through these technologies can help us address our scientific questions. With this question, and in collaboration with Dr. Feng Wang's team, we developed a hierarchical behavior analysis framework based on the AI-driven tools and the theory of estimate structures. This framework constructed the behavior into the minimize the posture and the movement formed by sequential posture over time, and cluster sets composed of similar movements, and the internal logic among the movements and the cluster. We call it behavior patterns. This framework enables a rapid identification of the states, behavior states, and elaborate to this composition of the behavior structures through marked-free recognition and posture estimation and adaptive learning, and then we use the hierarchical analysis. To establish this system, we choose the most fundamental and wild natural behavior, the spontaneous behavior. We systematically characterize and analyze the spontaneous behavior of mice over 1 hour, and both acute stress and naive control conditions across the different time and the different lightning settings. Through them, we identified 5 types of movements, including the scratching, which is unique to AS mice. We cannot observe that in the naive mice in any times. And then the features derived from the high dementia reduction to the low dementia revealed a difference between the movement sequence and posture expression profiles, and the movement scores distributions, and their feature spaces between AS and naive mice. And then we also identify the typically dynamic anatomic differences in several postures, such as the lower back height during the locomotion, and a more curling torso when they exploring. Moreover, compared to the naive mice, the AS mice showed a significant difference in many of the movement fractions. In this, the sniffing and grooming, which represent to the exploration to the external environment, and the focus on themselves grooming, they are the most abundant and significant alert in the AS mice. And we calculated the sniffing to grooming ratio and found that this ratio can exactly distinguish the AS mice from the naive mice across the 4 other states. Furthermore, we found that the many movements show their very strong temporary dynamics, and the time-related travel distance and the behavior similarity, also differences between the AS mice and the naive mice. Moreover, using a data-driven method, we identify a spatial preference of mice in the open field. The AS mice prefer the corner in the first 10 minutes, but swift to the center in the following 15 minutes. And the sniffing to grooming ratio in the corner within the first 10 minutes is enough effectively to differentiate the spontaneous behavior states of the AS mice from the naive mice. Further, we would like to investigate whether if there are internal logic of spontaneous behavior can be captured in our systems. By calculating the movement duration and their transition probability to the subsequent movements, we found that the behavior patterns of the movement and the cluster in AS mice also show a significant difference from the naive mice. Moreover, in both naive and AS mice, the most critical transition nodes was sniffing, indicating that exploration of the external environment is a co-driver of spontaneous behaviors in rodents. Moreover, using a movement transition and their duration probabilities, we generate a simulated behavior sequence. And this sequence can closely reflect the movement characteristics of real animals. And then, by swapping the dynamic movement duration probabilities between the naive and AS mice, we found that the behavior patterns are primarily determined by movement transition probabilities. And multiple innate drivers can shape the dynamic of network of the movement transitions, which can be influenced by the internal and external states. This system also exhibit a high transferability, and because it can enable the accurate differential between the wild type, the heter, and homo Jesus literature of the Shanxui autism model mice through the most spontaneous behavior detections, which traditional methods cannot achieve. Moreover, this system also has high visibilities, and our team has developed a system for the visual defensive behavior. Based on these systems, our data indicate that the under-visual threats stimulate both the male and female mice exhibit same ability to process the survival threats, but their strategy is quite a difference. This suggests that there are sex differences in the neuromechanism regulating the visual innate defensive behavior between the male and female mice. Built on this, our team is committed to refining AI-driven behavior system and systematically mapping the natural behaviors and investigating their neuromechanisms, and to support the new drug screening and evaluation of the novel disease animal models. I would like to thank the key contributors and the collaborators and the founders. And thanks for your attention. Any questions are welcome. Thank you.